Worst Fest starts Friday. Okay, 3.1, Extrema on an interval. So let's kind of analyze the title. Extrema, we learned that in pre-cal. What is extrema? Yes, this is the plural term for maximums, and minimums. So you have two types, maximum and minimums, but you also have two types. You have global or absolute, versus, if it was a competition, local/relative. So you have global extrema or absolute extrema, and you also have local extrema or relative. Usually when we pair them up, we pair up local and global and absolute and relative. Okay, but extrema is just an extreme value. And when we talk about extreme values, we're talking about y values. So extreme y values on what type of interval? X intervals, yeah. So we look from left to right on the x-axis, and we look to see where we have extreme maximum or minimum y values. All right, so let's go ahead and define what an absolute or a global minimum or maximum is. All right, so let's say we have some function on some interval I. It could be an open interval, it could be a closed interval, half open, half closed. Then we know that there is an absolute maximum or a global maximum if and only if f of c is greater than or equal to f of x for all other x in the interval. We would call f of c the maximum value. So what does that mean if f of c is greater than or equal to f of x for all other x? Does it mean necessarily that it's the biggest y value? What is the greater than or equal to? What does the equal sign mean? It could be a constant, right. So we kind of make room for the fact that it could be a constant. So you might want to read this as f of c is the maximum value if there are no other values bigger than it on the interval. Okay? If there are no other values on the interval bigger than f of c, then f of c is the maximum. Now also notice the way that I wrote it. You can call the maximum value the absolute maximum value. You can call it the global maximum value. But what do you know from your English class or your reading if something is in parentheses in front of a word? You don't have to have it, right? It's an optional qualifier. So what that means is if you just say that the function has a maximum value, everyone's going to interpret your meaning as an absolute max or a global max. So sometimes we say absolute or global just to clarify, but if you don't clarify, it's defaulting to an absolute maximum. Very similar then, you have an absolute minimum or a global minimum or just a minimum on the interval if f of c is less than or equal to f of x for all other x in the interval. That doesn't necessarily mean it's the lowest y value, but there are no other y values on that interval that are what than it? Smaller or lower than it, yeah. So we do make the allowance for constants. Okay, let's take a look at example 1. The easiest way to spot max and mins are from a graph. So we have this function given below. We're looking on the closed interval from a to f. So that's all the way from this point here to this point here. Do we have a maximum? Yes. Where is it? Yeah, is D the maximum? D is the maximum? D is an x value. How can an x value be a maximum? I thought max and mins were y values. Very good. You got to be careful. The maximum, we'll say we have a max of f of d at x equals d. G of d, not f of d. Very good. Sometimes I trick myself. G of d at x equals d. Okay, so we would say then there's no other y value on that interval that is taller or above that guy. So he's the absolute maximum. He's the global maximum. He is the maximum. And what about mins? Do we have a min? G of A? Yeah, I like that. We have a global min or an absolute min or just a minimum of G of A at x equals A. Now let's look to see what types of points they can occur at, because this is another big part of this section. The maximum occurred on a hill, right? What's the value of the derivative right there at D? 0, right? So the maximum occurred at a place where the derivative was 0. The minimum occurred, what's the value of the derivative at A? D and E, okay? Because it's an endpoint. So we already have an idea of where absolute extrema or global extrema can occur. They can occur at a place where the derivative is 0 or where it's undefined at an endpoint. Does this guy right here, does he have a shot at being an absolute max or an absolute min? No, poor guy. On that interval to the right, there are values bigger than he, and to the left, there are values smaller than he. So he's just a big absolute nothing, right? Sorry. Sorry, dude. Okay? You should have been born on the hill or at the end point, right? Those are the only two. And you can only have one. If you say there's a maximum value of, that has to be the only one y value. Now, it can occur at different places, like the graph of sine of x. At the top of the amplitude, the maximum is 1, but it can occur at many different places. But that's why we call it absolute or global max. There can be only one, if any, and it can occur at a place where the derivative is 0 or undefined at an endpoint. All right, so that was doing it with the graph. Now we're going to do example 2. I'm not giving you a graph, I'm giving you the equation. It was very helpful to have the graph, so that's actually going to be the way we're going to answer this. If f of x is equal to x squared plus 1 on the closed interval from -1 to 2. Step 1, draw the graph. What's your parent function? X squared plus 1. We know that that's going to be moved up 1 unit. And here's -1. And I'll come over here to 2. We want to know where this graph starts and where it ends. So what is the limit as x goes to -1 from the right-hand side? In other words, what y value does this pick up at -1? 2? Okay, I like that. So there's 2 right there. And what y value does it end at +2? 5. Yeah, 5. So I got to extend up my y-axis 2, 3, 4, 5. There we go. So at 2, 5. And of course we know it comes through the point 0, 1. Looks something like that. All right, you might want to copy that with scissors because we might need it on another one. All right, so now that we have the graph, it's a closed interval. Do we have an absolute min or a global min or just a min? Yes, we have a minimum of what? 1. Now, sometimes you can put y equals 1. When you have f of a or f of g or g of e, whatever, that kind of means it's a y value. Sometimes you can clarify by putting a y value in front of it. But if it follows the word of, it better be the y value. So we have a minimum of y equals 1 at x equals what? 0. So whenever you say at, you're talking about the x value. Very important. Of is the y value, the actual min, and at is the location, the x value. So let's see. It occurred at the vertex. What's the value of the derivative at the vertex? 0. So that's twice now that we've seen an absolute extrema occur at a place where the derivative is 0. That might be kind of important later on. Does this function have a maximum? Yes. What is it? It's a max of y equals 5 or just 5. You don't have to put y equals. It has a max of y equals 5 at x equals 2. What's the value of the derivative at x equals 2? On this closed interval, it's d and e, right? Because it's a what? An endpoint. So that's now the second time we've seen an absolute extreme value occur at an endpoint. I'm starting to think that absolute extrema can occur at x values where the derivative is 0 or where it's possibly undefined like an endpoint. What about this guy here at 1.5? Did he have a shot at being an absolute anything? If you throw nothing in there, he could, right? He's an absolute nothing again. Because to the right, there's values bigger. To the left, there are values that are smaller. Okay, sweet. Letter B. What's the difference between letter A and letter B, besides B comes after A? Open interval. All right, so let's go ahead and paste our picture from the first one. And now at the endpoints, we'll just make them open. There we go. So now we have an open interval. It's still an interval. Do we have a minimum? Yeah, did it change? No, we have a minimum of y equals 1 at x equals 0. What about the maximum? Do we have an absolute maximum now? We don't. We know that the limit of the maximum is 5. But does the graph ever get to 5 with an open circle there? No. How close does it get to 5 without actually getting there? Infinitely close. So when we say there's a maximum value, we mean definitively there is a single y value that you could stand on such that no other y values are bigger than it. So if you stand at 4.999999999, how many values are above you between you and 5? Infinitely many. Good. So there would be no max. Right? We still have our max, but on this graph there's no max. Right, Max? Right. Okay. No max. So let's see. Endpoints were kind of important to have, wasn't it? Because endpoints could be absolute extrema, and here we didn't have endpoints, so maybe having endpoints on the interval is kind of a prerequisite for being guaranteed a max and a min. Would you agree? Yeah. Okay. Letter C. What is this one going to look like? We're back on the closed interval, so paste. But now it's going to be x squared plus 1 everywhere except 0. So at 0 at the vertex, now we put an open circle, and it's defined to be the number 2. All right, do we have a maximum? Yeah, we're back to having a max of 5 at 2. And notice I didn't put y equals or x equals there. We have a maximum of 5 at 2. Do we have a minimum now? No, there's no min. And by min we mean absolute / global. Because I took away the y value where the derivative was equal to 0, I took away the place where the min is. So if we're trying to decide under what conditions we're going to be guaranteed to have both a max and a min, it would appear that we need to have the endpoints intact, since those are possible, local, or absolute extrema, and we would need to have vertices intact because they're possible max and mins because the derivative there is 0. That's what we're working towards. All right, letter D. Go ahead and paste it. Now we're not using 0 again for the parabola, so it's an open circle. But now we're defining it to be 0. Do we have a maximum? Yeah, we still have a maximum of 5 at 2. Do we have a minimum now? We do have a minimum. We have a minimum of what? 0 at 0. What's the value of the derivative at 0? Undefined, right? Not because it's an endpoint, but because it's not continuous. So that's the second variety of places where the derivative doesn't exist that could be local or absolute extrema. So it would appear then we need endpoints intact, and we need to have all the places where the derivative is undefined intact. Okay, they need to have values there, whether they're like this with a hole or an endpoint. All right, so we're done with that one. Let's move to sine of x. Sine of x from 0 to 4 pi. That's how many cycles of sine? 2, right? There's 4 pi, 2 pi, and you can just bisect it. So you go up to 1, down to -1, axis high, axis low, axis high, axis low, axis. Looks like that. Do we have a maximum? Yeah, we have a maximum of, I'll put y equals 1 here, at x equals where? The first one is pi halves. The next one is a full 2 pi away, which would be at 5 pi halves. What's the value of the derivative at both of those places? 0. Kind of an important location where the derivative is 0. So again, we only have one maximum value, y equals 1, but it happens at 2 different places. Do we have any mins? Yeah, we have a minimum of y equals -1, and it occurs at x equals 3 pi halves and 7 pi halves by symmetry, 1 cycle away. So only one min, but it occurred at 2 places. All right, last one here, 2 minus 3x on the closed interval from -1 to 2. That's a graph of a line. What y value does it start at x equals -1? 2? If you plug in a -1, you get 3 plus 2, which is 5, yeah? And if you plug in the 2, you get 2 minus 6, which is -4. So if you draw it, connect the dots, there you go. On this closed interval, does this function have a maximum value? Yes. It's what? 5. Good. At x equals -1. Does it have a minimum? It does. It's a minimum of -4 at x equals 2. So notice this graph on this closed interval doesn't have any places where the derivative are 0, but it did have both an absolute max and an absolute min, and they occurred at the endpoints. What if I did the open interval from -1 to 2 and I didn't include the endpoints? What if those were both open? Would it have a max or a min? It would be neither. Yeah. So I think we have enough evidence here to say, all right, what is required of our function if we are going to have a guarantee of both a maximum and a minimum value on an interval? Can we say anything? If we want a guarantee of both a max and a min, what conditions do we need to have? Has to be a closed interval. Has to be a closed interval, and then it needs to be what? Continuous. Good. Because if it wasn't continuous, if we had disruptions in the graph, like on part D or part C, it could work out to our disadvantage that we wouldn't have a min. So there you go. Oh, f of x equals 3. I forgot. There was this guy. Let's not forget him. What does the graph of f of x equals 3 look like? Horizontal straight line. Yeah, we're going from -2 to 4. Does this one have a maximum? Yeah, it has a maximum of y equals 3. Where? Yeah, for all x on the interval from -2 to 4. This is why the equal sign is so important when you define it. You're not going to necessarily say 3 is the biggest value, but on that interval there is no value bigger than 3. So 3 is, by definition, the absolute maximum, and it occurs everywhere. Do we have a minimum? Yeah, we have a minimum of y equals 3. And again, it occurs for all x on the closed interval from -2 to 4. And it's because it's defined with the equal sign. It's not that 3 is necessarily the smallest value on that graph, but there is no value on that graph smaller than 3. So it is, by definition, the minimum. So the minimum and the maximum can be the exact same value in the trivial case where you have a horizontal line. Okay, so here we go. This is called the extreme value theorem. Remember we had the IVT? This one we can abbreviate the EVT. And it's another value theorem. And it's very important. Here's what it says. If f is continuous on the closed interval, that's it. What was the if part for the IVT? If f is continuous where? On a closed interval. It has the exact same if as the IVT, the exact same if. So the IVT said if f is continuous on the closed interval, then y takes on every value between f of a and f of b. And there's an x value that generates it. The EVT, extreme value theorem, says if f is continuous on the closed interval, then f has both a max and a min value on the closed interval. And by max and min, what type do we mean? Absolute or global. There you go. So our evidence up here kind of indicated that, and now we have it in a theorem. So if a function is continuous on a closed interval, there's a guarantee that it's going to have both a max and a min. They could be the same value, but if they're not, we also kind of know now that they could occur only really at one of two places. Where? At an x value where the derivative is 0, or where it's undefined, DNE, like an endpoint or a discontinuity. Okay, but of course, if it's continuous on the closed interval, we wouldn't have the discontinuity. Here are some examples where the EVT applies. Continuous on a closed. It's going to have a maximum of f of c and a min of f of d. They occurred where the derivative was 0. Here's another one that's continuous from a to b. It has a absolute max at c and an absolute min at b, an endpoint, and a place where the derivative is 0. And here's another one that's continuous from A to B. It has an absolute maximum of f of c at C and D, and it has an absolute minimum of f of D. All right, so example 3. All we're doing here is we're going to see if the EVT even applies. Okay, does the EVT apply? Which means we're basically checking for continuity on the closed interval. Is the function continuous on the closed interval? Letter A. Is this function continuous from 1 to 2? No. So the EVT does not apply. And you would say since or because f of x is not continuous on the closed interval from 0 to 2. There's actually what type of discontinuity at 1? A jump, right. Now, just because the EVT doesn't apply doesn't necessarily mean you won't still have either a max or a min. There's just no guarantee. Does this function on the closed interval from 0 to 2 have a maximum value? No, it shouldn't, right? Because it would be the first number less than 3, because there's an open circle, and that's 2.99999. It doesn't exist. Does it have an absolute min? Yes, it has a minimum of 0 at 2. All right, letter B, does the EVT apply from 0 to 2? No, I'm just going to copy that and paste it. No. This one fails twice, right? There's a discontinuity at 0 and a vertical asymptote of discontinuity at 2. So this one's only continuous on the open interval, but at neither endpoint. It's not continuous. But it could still have a max and or a min. Does it end up having a max? Nope. It's unbounded as it approaches 2. So there's no max. Is there a min? Nope, no min. It gets infinitely close to 1 from above without getting there. Letter C. Does the EVT apply? From 0 to 2. Nope, it does not apply. There's a what at 1? A jump. Does it still have a max, though? Is there a max? Yes, it has a max of 3 at 2. Is there a min? Yeah, there's a minimum of, I'll just say f of 0 at 0. We don't know what it is. It looks like it could be maybe a half, but it could be 0.4, 0.45. So here's one where the EVT did not apply, but yet it still had a max and min. The EVT, remember, only gives you the conditions in which it is guaranteed to have both a max and a min. And then finally, letter D, does the EVT apply? No, again, it doesn't on either one of these. The function is not continuous on the closed interval. This one fails at both endpoints again. Do we have a max? Yes, we have a max of 3, and we don't know what the x value is. And do we have a min? Yeah, we have a min of, and we're not sure what the minimum value is either or where it occurs. But there is definitely a low point, and there is definitely a high point. So that's about as good as we can get without having more information. So again, the EVT did not apply, but yet it still had a max or a min. All right, so now we know the conditions where we're going to have both the max and min. The guarantee condition, continuous on the closed interval. But now we want to answer the question, okay, where can they occur? At what type of x values? So here's the definition. Very important. We'll be using this the rest of the year. A critical value. Critical value. Critical means what? Very important, right. But this is a definition. So in this class, a critical value is going to be an important value, but it is also going to be an x value. An x value on the function f that is in the domain of the function. Okay, the graph has to exist there. If the graph doesn't exist there, you can't call it a critical value. It has to be in the domain, and it's going to be the x value then where one of two things happens. Either the derivative is 0, that would be a horizontal tangent, or the derivative is dne. Okay? But remember, if the derivative is dne at that point, the function value is not dne. It's in the domain of the function. So that's going to look like something like this. It's either going to be like a hill or a valley, or it could be something like that or like that. Those are going to be the places where the derivative is 0 and the function is defined. If the function is defined but the derivative is not, it could look something like this, like a vertical tangent. It could look something like that. It can look like that. It can look like that. Or it can look even something like this. Or this. All right? As long as the function's defined, the derivative can fail to exist. Okay? So in the first two, the derivative would fail to exist because of the infinite slope. In the next two, it's because the slopes are different from either side. And in the last two, it's because there's a discontinuity. But again, notice the function value exists. If I were to take the dot away at the hole, now that would not be a critical value because it's not in the domain. So that's to first be in the domain, and then it's going to be the value of x where which things happen? One of two things. Either the derivative is 0 or undefined. Good. Now, if you take the whole thing together, the ordered pair, x comma y, then you have what's called a critical point. A critical value is sometimes called a critical number. Same thing. Critical number, critical value. Those are the x values. And if you write it as an ordered pair, then you have the critical point, critical value. All right, so here is another theorem. A lot of theory in this chapter. Absolute extrema or global extrema or just extrema in general can only occur at one of two places now. At a critical value, where the derivative is 0 or undefined, or at an endpoint of the interval. That's where the derivative is undefined, but it's a special one, so we'll kind of include it as a separate one. At a critical value on the interior or at an endpoint. So where can absolute extrema occur? At a critical value or an endpoint. That's it. All the other points are just going to be like big nothings again. So now we have a new way to find absolute extrema, kind of, right? Without the graph. All we have to do is find the critical values, find the endpoints, and if those are the only place where they could occur, I can then plug them in and find the y values at each and every one of them. And then the biggest one should be the max and the smallest one should be the min. We're going to play that game here in just a second. But not before we defined the other type of extrema. You have absolute global, and now you have relative/local. Notice these are not in parentheses. So if you want to refer to this type, you better either say relative max, relative min, or local max, local min. Because without the qualifying word, everyone's going to assume you're talking about global. So we're going to define this a little bit differently. If there exists an open interval containing the x value c, if there is an open interval containing c, that means that the graph has to live to the left of c and to the right of c. Can't be an endpoint, right? Cannot be an endpoint. Very important. If there's an open interval containing c, such that immediately to the left and immediately to the right of that x value, you have lower values, then the y value there is a local max. If you look immediately to the left and right of that x value and there's values that are lower, then you have just found yourself a local or relative maximum. In other words, if this is an open interval and you have an absolute max on that small open interval, then it's a local max. Similarly, you'll have a local or relative min if immediately to the left and right of that x value you have values that are bigger. Then you have just found a local max or a local min. So let's come back up here. This was the absolute max right there, but it's also a local max because if you look immediately to the left and right, you have values that are lower, so it's a local max. This one was the absolute min, but it's also a local min because immediately to the left and right, you have values that are bigger. What about this guy here at D? Could he be a local min? Immediately to the right, you have values that are bigger, and immediately to the left, there's nothing there. So an endpoint can't be a local max or a local min. Yeah, so up here, notice this guy. This was the absolute min. Was he also a local min? Well, let's see. You go to that point, immediately to the left and immediately to the right, you have values that are bigger, so that should be also a local min. So you can have local mins at discontinuities. The qualifier is you have to look left and right. What about on the dotted line or the straight line? Let's look at this value right there. Let's call that x equals 2. We know we have an absolute max at 2 and a local max at 2, or I'm sorry, absolute max at 2 and an absolute min at 2. But is it also a local max or min? Immediately to the left and immediately to the right, you don't find any values bigger. So it actually is a local max, and it's also a local min, because immediately to the left and immediately to the right, you don't find values that are lower. So it's still the same kind of criteria for an absolute max. So you can have local max and mins occurring at many different places on the graph, and they can be different y values. That's why we call them local. But there can only be one global extreme absolute leader, right? So here's the theorem now. We know that absolute extrema can only occur at critical values or endpoints. This one says relative or local extrema can only occur at critical values on the open interval. They can't be endpoints. Can't be endpoints. Okay, notice this theorem doesn't say that every critical value is a local max or min. If you look at these options right here, we have a local max and a local min, but right here at these other two, the derivative there is 0, but it's not a local max or min, because immediately to the left we have lower and immediately to the right we have higher. But it does give us a place to look for possible local extrema. All right, let's come back to example 4, and let's locate all the local extrema. So we've already done this graph with the absolute extrema. First of all, let's get all of our candidates. Where are our critical values? A? Is A a critical value? A lot of terminology here. All you have to be a critical value is in the domain, and the derivative is either 0 or undefined. Is the left endpoint in the domain? Yes. What's the value of the derivative there? dne. So it is a critical value. But is it going to be a local max or min location? No. So we got A, B, C, basically all the letters. A, B, C, D, E, and F. Those are all the critical values. Because the derivative doesn't exist at A, the derivative doesn't exist at F, and the derivative also does not exist at C. Notice the cusp? So they're all in the domain, so that makes them critical values. And then at B, D, and E, the derivative is 0, so they're also critical values. Now let's see which of those critical values, if any, are local max or mins. Let's just go from left to right and label them. Is A a local max, local min, or neither? Neither. It's an endpoint. Good. Still a critical value, but not a local max or min. I typically use local max, local min. At B, is F of B, the y value there, a local max, local min, or neither? Good. We have a local max. Remember, it wasn't the absolute max, but if you look on this relatively small interval, if you zoom in enough, you don't even know there's a hill somewhere else. That's why we call him a local max. In his municipality, in his relatively small interval, he's the biggest value. What about the cusp down here? Is that a local max, local min, or neither? It's a local min. Very good. If you were to zoom in enough, immediately to the left and right, you have values that are bigger. So that's a local min. It's a pointy local min, but that's okay. This guy here, is he a local max, local min, or neither? Local max. Remember, he ended up being the absolute max, but he still is a local max. This guy here, local min, or relative min. Wasn't the absolute min, but he still is locally. And then the right endpoint, neither. Now, if you go to college, you might get a professor that changes the definition of a local max or min, and he may say that the graph doesn't have to live on either side, and then he would call that a local max. But until that day comes, as far as it goes in this class, local extrema cannot occur at endpoints, okay? Neither. Neither. Great. Local extrema may not always be at nice, tidy hills and valleys. All right. So doing the same thing. Find all the critical values, and then determine if they're local max, mins, or neithers. First of all, critical values. I'm going to abbreviate that CVs. At x equals. Let's go from left to right. What's the first critical value on this graph going from left to right? -4. Good. Derivative there is dne. It's in the domain. What's the next critical value? -3. Good. Derivative is undefined. Function is. Next critical value. -1. Sweet. Next one. 0. How about all the values between -1 and 1? Because it lives on a horizontal line. At every point on that line, the derivative is 0. So there's infinitely many of them right there. What about 1? Can I include 1? Is 1 a critical value? Yes. Good. Next critical value. 2 and 4. Very good. Now, what if the dot over here at -3 were missing? What if there were no dot? Would that still be a local or a critical value? No. Okay? Remember, it has to be in the domain. That would still be an important point, but from the definition of a critical value, it's not a critical point. All right, so now we'll go from left to right, and we'll determine if they're local max, local mins. We'll just write it next to the point instead of listing it. Is -4 local max, local min, or neither? Neither. Okay. At -3, the y value is right here. Is that y value local max, min, or neither? Immediately to the left, there's lower, and immediately to the right, there's lower, so it's a local max. Yeah, local max. What about at -1? Very good, neither. You go to the dot, immediately to the left is lower, immediately to the right is higher. So there's neither local max nor min. Now, what about all the points between -1 and 1? Yeah, they're all local maxes and minses. So that's kind of the trivial case. On a horizontal line, 2 in this case is going to be a local max and a local min, and they occur everywhere. So what about at 1? Here's the y value down here. That's a local min. Good. Left and right, the values that are higher. Local min. What about at 2? That's a local, what'd you say? Min. Yeah, it is a local min. Yeah, immediately to the left and immediately to the right, there's higher. And at 4, to the left there's lower, and to the right there's nothing, so that's a neither. Good. I hope you all are getting the hang of this. A lot of theory, some definition, some theory. Absolute extrema can occur where? One of two places? Endpoints or critical values. Local extrema can only occur at a critical value. That's not an endpoint. Good, because endpoints could be critical values. All right, example 6. Find the domain and the critical values of each of the functions. So now we're going to be using equations instead of graphs. Find the domain. What's the domain of this function? All real numbers. It's kind of good to find the domain. So I know that this graph is defined everywhere. So how am I going to set out to find the critical values then? Critical value is where the derivative is either 0 or undefined. So I guess I'm going to need the derivative, huh? Let's find it. F prime of x. Multiply, you get 2x cubed minus 3x squared minus 2x. Is that function ever undefined? No. I would have you always find those first, because those are the ones that most students forget to check because it doesn't happen that often. F prime equals DNE? Never. So we don't get any critical values that end up being cusps or vertical tangents. But is it ever equal to 0? Possibly, right? Up to 3 different places. It's a polynomial. So once you say f prime is equal to 0, you're going to get a check. You're indicating the equation you're solving. Or you can go ahead and actually set the expression that is f prime equal to 0 to get the check. All right, so if we try to factor that, we'll pull out a factor of x first. It gives you 2x squared minus 3x minus 2. And then does that thing factor anymore? 2x and an x. Maybe a -2 and a +1. That works. So now you can list all the values that make it 0. X equals 0, -1/2, and 2. You can solve them in your head. If you need to set them all equal to 0 and show more work, feel free. But you should be able to look at those and just by the factor theorem rattle off the roots. So these are the three values that make the derivative 0. So are these all three critical values? Yes. So now I'll just say CV's at x equals. Now, do we know at this point if those are going to be locations of local max or min? Not necessarily. Remember, those are just the potential location of local max or min. We're going to have to get some more information if we want to know if those are local max or min locations. But we'll do that later. Right now, we're just focusing on finding critical values. All right. G of x equals 2 minus the absolute value of x minus 4. Is this one we can take the derivative of? Not unless we decompose it into a piecewise function, yucky, yucky, gross, gross. Or use the identity that the square root of x squared is the absolute value of x. Yucky, yucky, gross, gross. What can you tell me about this function? It's an upside down V for victory graph, right? And we know the derivative is going to fail to exist at the vertex, right? So if it's an absolute value function and it's linear, then remember the value that makes the inside of the absolute values equal to 0 is going to be the x location of the vertex, and that's going to be at x equals 4. So we do have a critical value at x equals 4. If you want to put it in the standard transformation form and sketch it, that's fine too. The vertex is going to be at 4, 2, and it's going to open down. So that's an easier way. Take the argument here that you're taking the absolute value of and just say it's equal to 0, and you'll find the coordinate of the x coordinate, I should say, of the vertex. So there's a critical value there. Now, because we know what the graph looks like, it is going to be either a local max or a local min. Slaughter already said that the graph opens down because there's a negative in front, so that should be the location of a local what? Max. Yeah, and it should also be not just the local max, but also the global max or absolute max, or just the max. All right, letter C, we'll stop right here for the day. Okay, wow, x to the 3/5. Let's take the derivative. What's the domain? Oh, by the way, the domain of this one was all real numbers. What's the domain of this guy? X to the 3/5 is the fifth root of x cubed. Are we allowed to have zeros and negatives under a fifth root? Yeah, as long as it's not in the denominator, and it's not. It's x to the positive 3/5. So this one should be all real numbers. There's not a single number we can't take the fifth root of. All right, so now we're going to need the derivative, which is going to require the product rule. So here we go. F prime of x is 3/5 x to the negative 2/5 times 4 minus x plus x to the 3/5 times negative 1. If you were to clean that up, you'll have 3 over 5 fifth root of x squared times 4 minus x. I'll throw that in the numerator. Plus the fifth root of x cubed with a minus sign in front. I'll change that to minus. So all you have to do to figure out where the derivative, bless you, equals 0 or fails to exist is to analyze the denominator or the domain of the f prime. Notice because it was 3/5, that's an exponent less than 1. When you use the power rule, you end up with a negative exponent, which threw the variable from the top to the bottom. And now we could still have negatives under the radical, not that we're going to because it's squared, but x cannot equal 0 now, right? X cannot equal 0. So is 0 in the domain of the original function? Yes, but is it in the domain of the derivative? No. So is it a critical value? Yes. So here's what you should do. Look out for in the future. If you have a fractional exponent less than 1, you're going to be on the lookout for a cusp, so cusp alert, or a vertical tangent alert, vert alert. And in fact, you can figure it out where it's going to be. It's going to be at the root of the base. What value when you plug it in for x gives you a 0? 0, right? If that were like the quantity x minus 1 to the 3/5, then it would be at x equals 1. So you should, before you even start, realize that there's going to be a vertical tangent at 0. Now, in order to figure out if there's another place, we'll have to get a common denominator and get a single fraction. Let's pledge.
Thank you. Attention students, this is just an announcement about tomorrow for Halloween.
If you get a common denominator, multiply by that over that, you end up with this. X to the 3/5 times x to the 2/5 is x to the 1st. Okay? So now you clean it up into a single fraction. A single fraction is equal to 0 when the numerator is 0. So the value that makes 3 minus 2x 0 is 3/2. So there's actually two critical values here.
Attention students with overdue books and fines. The library will be accepting a canned food item in exchange for your library fine.